Hi, good afternoon, everyone. I'm Tilina Hinadigal from Europlanet, and this week we are actually having a Europlanet summer school in Molite. Wait, how do you pronounce it? Molite Observatory in Lithuania, and it's been a very exciting week. But we were supposed to have a public talk by Dr. Eleni, and unfortunately she had an accident, but we do have her online, and which makes it actually accessible for everyone else as well. And so just a quick introduction to Eleni. She's an astronomer, and her research interest is in active and interacting galaxies, and at the same time she's quite active in outreach and communication in astronomy, which is quite rare where to see a researcher doing astronomy education. And today she's going to talk a very interesting topic called Inspired by Cosmic Space. There's going to be some music, some space sounds. Eleni, do you want to give a quick introduction to your talk?
Sure, of course. So first of all, maybe I would like to thank everybody for being there. And I would like to thank Europlanet, of course, for organizing this amazing school, and Gratina and all the local organizers, and Tilina, of course, for your help, and Anita. And it is great to be with you, but it is not great that I'm not in reality with you. It has been an exciting week on my end as well. So because of my leg, I cannot join you, but I'll try to be as lively as possible through this electronic media, through the distance. And this is actually an interesting experiment to see how much outreach we can do from a distance. So yes, the talk today is inspired by cosmic space. And of course, cosmic space inspires all of us in many different ways. What we will try to focus on this talk is the sounds of space. So whether we can understand space and everything in it, not only through our minds or through our eyes, but also through our ears. So what sounds we can hear, and what can these communicate to us from space. So that's what the talk is going to be about. Okay.
Great. So we can start with your talk, Eleni. I'm gonna.
Yes, of course.
Sorry, just
more sound.
Yes, Anita.
sorry. I'm sorry. Question?
You have more sound.
I think it's all right.
All right.
I think it's all right. Sorry, we're just saying hi to you from our team here at the Multi-Observatory. We have our students from our course who you could probably see in the background. We have Gražina, who's been hosting us here at the summer school and is the director of the observatory here. And we have some external people that we're very delighted to welcome here to hear Eleni. We're very, very sorry that you can't make it in person. We're very disappointed, but we are delighted that we can see you and we can share in your talk. At the end, we will be asking questions. You will have a chance to talk to Eleni. If people are listening online, then they can too submit questions via the chat or by tweeting Europlanet Media. And we're looking forward to a great discussion.
Thank you.
So,
Anita. Okay, let me share the.
Right. So this is the title. So let's get started with the first overhead. Great. Okay. So as I said, the talk is about inspired by cosmic space, or if you like, by universe. So let's say just a few introductory words. That's how the talk will go about. So we'll just say a few introductory words about what is within the universe, how we perceive those things, and then talk about the sounds, about sounds from space and what we can do about them and what we can understand from them. So what is universe? If we were to describe universe, we would say from an anthropocentric point of view that universe is everything that exists, ever existed, and will ever exist everywhere. You see already this is an anthropocentric view. So what we would say it's matter, it's energy, it's even time, it is galaxies, stars, planets, and everything else. Now, during the last hundred of years, great many discoveries were made, and people have discovered a number of things. For instance, one of the very important things is that they discovered that galaxies outside our own galaxy are moving far away from us. And the further they are, the faster they move out. So if you can play the video that is on the bottom of this page, just a little bit, just to see what I mean, right? So this is what we discovered. We all know that by now, and we are certain that this is the case. What we didn't know, and we also discovered relatively recently, is that the universe is expanding constantly, faster and faster. And with that, everything that is in it, including galaxies and ourselves. Let's move now to the next overhead. Right. Now, we know that the fastest speed in the universe that we know at least, is the speed of light. And this is about 300,000 kilometers per second. This means that this is a finite speed. This means that the light takes time to cross the universe. So in 1 year, the light will travel about 10 trillion kilometers. 10 trillion kilometers. In this respect, when we talk about light years that we have here talking about, is not a unit of time. A light year is a unit of distance. A light minute, for instance, it is about 18 million kilometers. A light second is about 300,000 kilometers. So we can say that the moon is about 1 light second away from Earth. Pluto is about 6 light hours away from Earth. The nearest star is about 4 light years away. The nearest galaxy is about 2.5 million light years away. And distant galaxies are billions of light years away. If we can move now to the next overhead, the question that comes naturally then is, okay, but how big is the universe? Well, the answer is that we currently don't know. We cannot determine that. It may well be that the universe is endless. What we do know is how big is the observable universe, meaning how far we have seen light coming from. And this number is the number you see there on the top. So it is 93 followed by 9 zeros, means 93 billion light years across. That's how far we have seen so far. Light from places further away did not yet have the time to come to us. So everything we're going to talk about today is coming from within this distance. Now, another thing that we need to know, because we're going to talk about the first sound we receive from the universe, is this diagram on the bottom. While we're explaining the diagram on the bottom, you can play the video on the top if you like. Okay, this is just to travel through space. So what we see on the bottom is the cosmic timeline. On your left-hand side, you have the so-called zero time. It is when the universe started with the Big Bang. That's what we accept the starting of the universe was. And as we move towards the right, we see time developing from the beginnings of the universe all the way to today on the right-hand side. This is the history of our universe. This is how far we can get. And within there, you can see at various scales describing what kinds of cosmic objects, if you like, have started being created. So we had the first stars, the first galaxies, the first black holes, and so on and so forth. If we move now a step further and we go to the next slide. Right. All of these things so far we know from only one thing, from light. Whatever information we get from space, we get it from light. And as you might have heard, sometimes we call light a wave, Sometimes we call it particles, sometimes we call it energy. So what is really light? Particles, wave, or energy? When in reality it's all of them. Depending on what we want to explain, how we want to use light, we can perceive it as a wave, we can perceive it as a row of particles, the photons, and all of them, particles or wave, carry energy. If you now go to the next slide, you can simply see on the right-hand side what a wave form of light looks like. So it's like a wave you see on top of the sea, on the surface of the sea, where you have the distance between two crests called the wavelength. And either wavelength or frequency. So frequency is like, if you could imagine, you are sitting and you see light passing in front of you, and you have a watch and you count how many waveforms are passing in front of you. The larger the frequency, the more waveforms pass every and each second. In this way, we define a whole spectrum of light, from the gamma and the X-rays, where you have the big energies, the big frequencies, and the low wavelengths, to the radio on your right, where you have the large wavelengths and the low frequencies. So later on, I will tell you that we perceive sounds from the universe, and we have to transform them to audio wavelengths. Well, audio wavelengths often coincide with the area of the radio wavelengths, which I just showed you before. I think we can skip this overhead and we can go ahead, since we talk about light. Okay, so question now, is there sound in space? We all know that space is empty, and we know that in order for the sound to propagate, we need to have something else than empty space. What do I mean by that? You see it in this overhead. So you can imagine of sound traveling through space in the same way that light does, as a wave, only that it has a very different speed, a much lower speed, okay, 340 kilometers per second. So, in order for the sound to travel in space, though, it cannot do it like light. You do have to have molecules. You do have to have some material. So for the sound to travel, it has to compress these molecules and go a step further. I will show you a video in a second about that. If there is nothing, if there is no matter there, you cannot have sound traveling. So if you can play the video on the top. So this is a kind of moving string. And if you move a string, if you touch a string with your finger and you hear a sound, and this sound is actually these waves that you see on the right, on the left, as the string is moving, it compresses the air molecules, and that is how this wave is propagating. So if you do not have that, then you do not have sound. If you can go back for a second. Right. So you see on the bottom the light, the sound waves. Now, in reality, the space, if you like, space between stars or even galaxies is not really empty. It has a very low density, but still it is full with stuff. And this stuff, it's usually gas and dust. So, and this is dense enough for some sound waves to propagate. So here we have to pay a little bit of attention. So first of all, the unit we use to perceive sound, to classify sound, is called hertz. 1 hertz is 1 oscillation per second. You remember I told you you have a watch and you are looking how many waves are passing in front of you. So 1 oscillation per second is what we call hertz. Now if we go to the next overhead, in order for the sound to propagate in space, you have to have the molecules, say, of the air, have to be at a certain minimum distance. So the average distance of two particles in the air, for instance, have to have at least the same length as the wave of the sound. If the wave of the sound is shorter and the two atoms are further away, you can understand that they cannot help the sound to propagate. So sounds with short wavelengths can be easily propagated when the medium is dense. When it is not dense, like it is in space, so only very large wavelength sounds can propagate. So that you in general know the human ear can perceive frequencies between 20 and 20,000 hertz. This means between 17 meters and 1.7 centimeters. If you can move now to the next overhead, let's see now, with knowing this information about sound, let's see what we can hear from the universe, how we can perceive the universe with our ears. Let's start from far away and move towards our solar system. The very first sound of the universe is a sound that followed the Big Bang. I will let this finish. So this is not the sound we hear, of course, from space. It is just a sound that is put there from the person who made this video. But what this indicates is the Big Bang, so the big original explosion which supposedly created the universe and everything else in it until today. We know that this happened about 13.7 billion years ago. 13.7 billion years ago. Now, the very first 760,000 years after the Big Bang, matter in the universe was extremely dense, so dense that light could not propagate freely. So it was an opaque medium. Light could not travel through. After that time, after 760,000 years, if you can go to the next slide now. Okay. After that time, the universe cleared up. Atoms were formed and cleared the path for the light to travel. So around this time, light was free to travel through space. And this very first light coming from the universe at that time, at 760,000 years, continues today to propagate throughout space. Have we seen these lights? Yes, we did. This is called the cosmic microwave background, and this is the oldest light ever coming from the universe. However, this is also the oldest sound recording of the universe. So if we take this light that we see from those times, which is now in the microwave wavelengths, and we multiply the frequency by a very large factor, by 10 with 26 zeros following, 10 to the 26, then we can make it audible to human ears. Remember, we said that the human ears can perceive only certain frequencies. So we can take this light from the early universe and we can make it audible to us. So if you would like to hear how the original sound of the very first sound of the universe sounds, you just have to move one overhead ahead. And now we can play this. There is a little bit of publicity, but doesn't matter. And there it comes. Here. In principle, you should be able to hear some sound. Good. So this is the very first sound of the universe. very low frequency, but we can make it audible to us. Let's move now a step further. If we can come closer now, but not much closer yet, we go to a black hole. The universe, as you know, is full of black holes, big and small. So if we stop about 250 million light years away, there is a group of thousands of galaxies. We call this a cluster of galaxies. And in there is a huge black hole. Now, this black hole has emitted the deepest sound we have ever heard. It is about, as I'm saying there, 1 million billion times deeper than the lowest frequency sound we can hear. And you remember we talked about it. Now, how this happens? If you can play the little video, I can explain in a second how does this work. Okay, so here you see a simulation of what a black hole is like. So very close to a very big black hole, you have gas, which is highly magnetized and rotates about the black hole, like you have the water swirling before it falls into the drain. So this material, as it is moving around the black hole very fast, it gets very hot. So hot that it actually ejects matter from two opposite sides of the black hole before it gets into the black hole. This is what you see. Now, if you move one overhead afterwards, okay, so now this swirling black hole actually emits waves. As you can see in those images, these waves were actually observed by Chandra X-ray Observatory. So this is a space observatory that is sensitive in X wavelengths, X-ray wavelengths. So those ripples are actually the relicas of these sound waves, if you like, propagating out of this black hole. And because this hole is very far away, what we receive is very, very low frequency. However, this can still be transformed to sound and be heard. So if you like, this is the oldest sound of a huge black hole 250 million light years away. Let's move a bit closer with the next overhead. Next thing, we enter our galaxy. Our galaxy is full of stars. All stars are not like our sun. Our sun is an adult star. However, there are stars which are reaching the end of their lives. One possible ending of life is what we call a neutron star. A neutron star is a very dense star. It's a very small star. It's about 20 kilometers across, like a big city or an asteroid, a typical asteroid maybe, but its mass is more than the sun. So you can imagine the whole sun being squeezed into the size of one Earthian city. This makes it a very, very dense star and actually a star with a very high magnetic field. This, if you can press the button so it can show some more information. Okay. So this is such a dense star that if you take a human who weighs about 70 kilograms on Earth and you put him or her on a neutron star, it will weigh about 1 billion kilograms. Okay. Now these stars are actually rotating, spinning very fast, and as they do, they flash radiation towards the whole universe. And if the Earth happens to be in the light path of this flash, then we can actually see this star pulsing. If you go to the next slide, okay, and you push once more the button, okay, that is what a pulsar would look like. Now, these pulsars can be heard and they can have very different frequencies. So what you see now is frequencies. You are told what is the frequency, how fast a pulsar is moving around this axis, and then you can hear the sound if you shift it to the audible frequency. So this is the sound of a pulsar with relatively low frequency. We can move to a pulsar now with a higher frequency. a lot of time to settle around itself. And the image actually shows how this is. Okay. You can hear one more and then we can move to the next slide because I have too many pulsars here. So this is a famous crab pulsar. Right. So this is what the universe sounds like away from our solar system. Let's now move closer and talk about our solar system. Our solar system has planets and has smaller bodies. First of all, it has planets and minor planets. Then it has comets. It has asteroids and smaller material which is floating around space. Let's try to hear our own solar system. What does it sound like? First of all, let's go to some of the planets, okay? What I'm saying here is that lightning is a phenomenon which we are very familiar with on Earth, in the Earth's atmosphere, during a thunderstorm, for instance. What we didn't know, but now we do, thanks to our observatories, ground-based and space-based observatories, we know that lightnings are occurring also on other planets, planets with atmospheres, for instance, Venus, but also on the giant planets like Saturn or Jupiter. What I'm also saying here is that some of these lightnings have been recorded, for instance, with Juno. Okay, so what I'm going to show you in the next overhead is a spectrogram which indicates the frequency and the time, and then you can hear actually the sound coming from lightnings occurring on Jupiter. And actually, it's the sound is getting stronger when you go through the bow shock in the atmosphere of Jupiter. So you can play that. It's quite impressive, I think. Let's move. Excellent. Let's now move to Saturn. Another phenomenon that occurs, we're going to talk about that on Earth in a moment, but another phenomenon that occurs not only on Earth, but also on other planets is the phenomenon of auroras. Okay, maybe we don't see auroras here in our southern wavelengths, but in the northern wavelengths, in the southern geographic latitudes, but in the northern geographic latitudes, you certainly can see beautiful auroras. So beautiful auroras, the northern lights or the southern lights, are also seen in other planets. For instance, in Saturn. One of those have been detected, or many of those have been detected by the Cassini spacecraft. And so here, what I want you to hear is how these amazing emissions are sounding if you shift to the proper frequency so they become audible. So if you can move to the next overhead, and you can play that, then you can see how auroras are sounding on Mars, on Saturn. Great. Okay, I think this is quite a spooky sound. I think I would be quite scared if I was out there by myself listening to this. Let's hear now some other sounds. Let's go on the left where there is Io. So this is Jupiter's, one of Jupiter's satellites, and let's try to listen to the sounds of Io. And this comes from the Voyager passage, so it's quite old data, but still they're quite amazing. Okay, so as you are going to see also with the Earth, these sounds now are not related to an atmosphere on Io, are just related to the interaction between the solar wind. The solar wind, as we're going to show in a second, is a wind, if you like, of particles, of plasma, of very highly ionized particles that travel through space. And when they meet the magnetosphere of a planet or of a solar body, then they interact with it. And by this interaction, you have the production of electric signals, which they can be transformed to audible sounds so that we can hear them. And that's what happens with Io. If you can go on the bottom of the lower now video. Similarly, we have sounds coming from Neptune. And on top, from Pluto. Excellent. Let's move to the next one. So what can we understand from all this is that the universe is resonating everywhere from one edge to the next, whether it is far away from the beginnings of the universe all the way to our solar system. If we just were having the proper ears, sensible in radio wave wavelengths, then we would be able to hear a very loud universe. Let's now move closer to home. Now, if you can go back for a second. We can have sounds that come, of course, from the atmosphere of the Earth, like the lightnings, for instance. We can have sounds that come from the interaction of the atmosphere with the solar wind, for instance. We're going to talk about them. But before that, we, of course, can have sounds that come from the surface of the Earth, from human activities, but also from the depths of the Earth, from the depths of our planet. So let's start from there. Let's start from the depths of the Earth. What I'm saying here is that if you have an earthquake, you are actually producing vibrations. You have waves propagating on the surface, on the within and on the surface of the Earth. This comes in contact with the atmosphere. So those waves are propagating out through the atmosphere, and then they are moving upwards and upwards. And we said that this imitates sound waves as well. But then, for as long as they are atmosphere, then you can actually see those sounds propagating, those waves propagating. If you go to the next overhead and you play the little video, you can see how this happens with a real earthquake that happened in Japan, a very large one of in the scale of 9, that happened a few years ago in Japan. So this, you see the waves propagating on the surface of the Earth. And now you can see that these waves are actually propagating further in the atmosphere. And if you have something flying in the atmosphere, like for instance the satellite, the Kochi satellite, which was already 270 kilometers from the surface, You can feel those waves. And you can hear them, of course, if you do the job as before. Let's move now further. Okay. Now, as I said before, in the atmosphere of the Earth, you have several sources of sounds, lightning, but also interaction with the cosmic space. What I'm saying here is what I said before. If instead of ears we had radio antennas, we would be able to hear all these sounds. We don't have that, so we have to use receivers for this very low frequency, lower than we can hear waves, and then we convert them to electromagnetic waves in the radio frequencies, and then we shift them to the acoustic frequencies, and then we can hear. We call all of them Earth songs, but they can be very different, and we're going to hear a few of them and see how they are produced in the atmosphere of the Earth. So if we can move now to the next overhead. Okay, so we have, for instance, first the whistlers. So the whistlers, as I'm saying here, are produced by lightning, and they travel along the Earth's magnetic field line from the one hemisphere to the other. So our planet is like a huge magnet, and you have the magnetic field lines propagating, coming out from the one pole and going in the other pole. So you have those waves propagating along and turning around along these magnetic field lines. So if you would like to hear these kinds of waves, these whistlers, we just have to go to the next overhead. And you can play that.
Earth whistlers.
Let's go to the next one. Okay, these are somewhat different. They are called proton whistlers, and they can be detected further up in the atmosphere of the Earth in a part of the atmosphere which is called ionosphere. Okay, if you go to the next overhead, okay, you see the difference. Whistler on the left, which goes down with time, so the frequency gets lower with time, and proton whistlers, which have a very stable frequency. They're quite different, and you can see the mechanism by which they are produced on the top, okay? So you can play that now.
Earth proton whistlers.
Okay, I think that's enough. We got the idea. Let's go to the next one now. Let's move on. Okay, then we have the chorus waves. So these are generated in a special part of the Earth's atmosphere, which are called Van Allen radiation belts. And here you have again the magnetic field lines of the Earth, and now you have electrons that are spiraling along these magnetic field lines, okay? So what I'm saying here, I'm describing the chorus waves, the rapid succession of intense ascending tones, rising in frequency instead of falling, over very short time intervals. Okay, if you would like to hear them, then we can move ahead.
Earth
and you can play them. So these are like bird-like. Sometimes we describe them as bird-like sounds. You can move cosmic birds. You can move to the next. Okay. And then you have, you remember I told you about auroral radio emissions. So now I'm using this video to show you how you create auroral emissions.
Winter sky.
And actually this indicates, you have to go back. Right, we can play the video, the previous here, on the bottom. So you can hear how the sun, you can see how the sun interacts with the Earth's magnetosphere.
On Arctic nights, the aurora often flames across the winter sky. What is it, and where does it come from? This is where the tale of the aurora starts. On the sun, a star of average size among billions of other stars in our Milky Way.
The sun's energy and radiation.
Is an enormous power plant. The energy is created deep inside the core of the sun. Here the temperature is over 14 million degrees, and the pressure so enormous that hydrogen atoms are squeezed together into another element, helium. This nuclear reaction releases energy. The light radiates outward from the core of the sun. In the outer layers, the heat moves to the surface in huge eddies called convection cells. These electrical currents of charged gas create magnetic fields inside the sun. In some places, strong magnetic fields push their way up through the surface. They slow down the eddies of hot gas. The surface cools, and darker sunspots appear. The electrically charged gas is called plasma. The plasma drags the magnetic field further outwards. The magnetic field stretches and twists like a rubber band, and then the rubber band breaks. Several billion tons of plasma is hurled out from the sun. This is called a solar storm.
So if you take now this amount of material that came out from the sun, and you follow it throughout space,
After 6 hours, it moves past the planet Mercury. After 12 hours, the planet Venus. And after 18 hours, the solar storm reaches Earth. When the solar storm reaches our planet, something strange happens. An invisible shield, the Earth's magnetic field, deflects the storm. The magnetic fields couple together and create a funnel where the gas streams down on the daylight side of the pole. This is the daylight aurora. The magnetic fields stretch further back and couple together. The magnetic rubber band breaks, and gas from the solar storm streams along the magnetic lines towards the poles on the night side. This is the nighttime aurora.
okay, so this was a good explanation of our auroral section. Excellent. Excellent. So if now we want to hear those alarms, so the emission of those electrons, radio wavelength, you can just push the button.
Earth, auroral kilometric radiation.
Excellent. Let's move further. So far we have seen that all objects in space, the sun, the planets, the stars, the black holes, pulsars, even the universe, are actually producing signals that, if they are received in the proper wavelength range, they can be perceived as musics. So people have noticed that, or have imagined that, even in ancient Greece, you know that Pythagoras was talking about the harmony of the spheres. So he believed that the planets and the stars, the way they are moving in the universe, they are actually following the same mathematical equations as the music can be described with mathematical equations. So he actually made this correspondence between the movement of the planets and the musical notes. So he imagined that the planets, as they are moving through space, they are producing a kind of a symphony. So, of course, they did not have the possibility to measure or to hear those sounds as we did here today. However, they could imagine about that. And so people have liked to imagine that the universe is actually talking to them through sounds. If you move to the next overhead, okay, this idea was further explored in the Western history. And even recently, we know of some well-known and some less well-known attempts of people to create music from the original space sounds. I'm mentioning here the Planets by Gustav Holst because this is what is a well-known example of being inspired by planets, even though here we didn't use the original sounds of the planets or the stars that I mentioned before, or I mentioned, for instance, Dave Bowie. However, there have been many other attempts where people actually use the original sounds to create music. So if you can move in the next overhead, we can see some of those, okay? So there was one of these examples that I'm going to mention is this musical work which was commissioned by NASA on the basis of radio waves. And this piece of work was called The Sun Rings and was performed by the well-known, I imagine, Kronos Quartet, the chamber music. So this work, which we're going to hear in a second, includes sounds collected over a large period of 40 years by scientists using various space instruments, space missions, Voyager, Galileo, even Cassini, who captured those signals, transmit them to Earth into sound, and then were used to inspire people to create this music. So if you can play this video now. Okay. So this was quite original. Nevertheless, you notice that this music was interpreting the space sounds, not using them originally. So let's move to the next overhead. Okay. There are other cases, like for instance this one. So this was a team of researchers, again, who actually used data, but now from something different, for a binary star called Kepler 466, etc., which was actually observed by the Kepler space mission. That's why it has this name. And so they used, so this is a binary star, two stars together, which move around each other. And as the one obscures the other, the light goes down and up, so it's dimming and brightening. And they use this information actually to create music out of this, okay? And if you would like to hear what this sounds, we can play in the next overhead. You can play that. So this kind of cosmic music was used for the introduction of this piece of work.
تحياتنا للأصدقاء في النجوم يا ليت يجمعنا الزمان. Hello for the children of planet Earth.
Okay, that was the introduction. Now it's the full music. So we can move ahead. Okay, we can move to the next one. Excellent. So here you could see in the beginning, there was the first real time where you can see merging the human creation with the nature's creation, the two sounds together interpreted by humans, which I think it was quite, I like it very much. I like that one very much. And of course, there are many more attempts, and not only to create music, but here, for instance, I picked this up on the internet. I didn't know about its existence a few days ago. So this is a kind of short film competition for filmmakers, where they have to make videos featuring inspired by sounds of space, so original space sounds coming out from satellites, from missions. And so there are actually prizes offered for this. The deadline was a few days ago. So people are certainly being inspired by these space sounds. If you can move now to the next overhead. So what I'm going to finish this presentation with is a similar kind of competition we ran a few years ago, and we intend to continue running in the future. So this was in the framework of a EU-funded project, which was called Marble, which was actually a scientific project dealing with monitoring waves in the Earth's Van Allen zones, which were created from the interaction of the solar wind and of the solar storms, which we saw in the video before, with the Earth's upper atmospheric layers. And so the sounds that were produced there were mostly low frequency sounds and were recorded. And by recording those waves, you can actually monitor the activity of the sun and the so-called solar weather, which directly affects the Earth. So it has a scientific value, which is very important. As a byproduct of this, though, we thought of actually using those waves, which were recorded by this project, to inspire musicians to create electroacoustic music. And so there was this contest open to the public and to all countries in the European Union, and also USA and Canada, because these were the countries participating in this project. So if you can move ahead. Okay, so here you can have the link. It's still valid, even though the project has finished a few years ago. And so we use data, we offer data from Charisma, And we had at least 50, more than 50 applications from 17 countries. And it was a very difficult task. They were all excellent. So it was a very difficult task for people to actually choose the best of them. And the best of them were, of course, offered some prizes. So on this website, we have still indicating the 10 highest ranked compositions and the 3 winners. And by clicking on the links, you can actually hear the music they created, which was quite amazing. If you move to the next overhead now. Okay, so you have these 10 high ranked people, and if you move one further, you can have the 3 winners. You can see that the titles of the compositions are quite original: Breathing Underwater, Picnic in the Ionosphere, and Golden Waves. And if you would like to hear what they sound like, of course, they're very long. They're about 5 to 10 minutes each, but we can hear just a few seconds of each. You can click on them. I don't know if you can click on them. If you have internet connection, you can actually hear. Yes, you do. You can advance ahead maybe a little bit, I don't know, within the, yeah, just move it a bit further. No, you can't hear much. You cannot hear it very well. Can you move to the second one maybe? Try it again and try to move it further in the middle, more or less, of the piece, so you can hear, yeah, something like that. You hear now something? No, it's very bad. Okay. I think that's good enough. Good. So all of these people, yeah, I don't know if you want to try, yeah, you can try that one as well. You can try the golden waves of smooth. We can't hear that one either. I don't know why. It's okay. Doesn't matter. We got an idea at least. So if you want to hear those, you can go to the website and then hear one by the one after the other. Not only those 3, but all the 10. So you can see how many different interpretations and how many different inspirations people got from these sounds. There were quite a few sounds, like 30 sounds. So they had a lot of possibilities to combine and create them. And actually, they create full stories behind them, which they described in words. And I thought it was quite moving and amazing how these people could be inspired with whole stories about what they could hear. Some people could hear sounds from space. Some people could hear other people talking in space. They could hear extraterrestrial life. Some of them, they could hear some universal harmony, and so on and so forth. So, unlimited inspiration from those sounds, and this came out very nicely in this beautiful music that they composed. If you go to the next overhead, okay. So of course they got some prizes. Those people, please move ahead. And here I'm just showing that it got quite an impact publicly. So it was produced, and people have been talking about that in quite a few meetings afterwards. And if you can move ahead. Okay, this was clearly a source of inspiration for many different people. First of all, for the public, we have been producing those sounds together with showing beautiful images and describing the phenomena which create these sounds that then inspire people. And so this has a very strong value for outreach, because in this way, people actually, like we do today, get to feel what universe is like, not only try to understand it logically, but try to feel the results. So if I was talking about all these phenomena to you today, like pulsars and black holes and the relic radiation from the microwave background and the auroras or the lightnings in Jupiter's, for instance, atmosphere, etc., you would have heard me. You would have tried to understand what I'm saying, but you wouldn't have a feeling about it. And by trying to play in parallel as fast as we did today, which was very fast, but by playing those sounds, you got a feeling about that. You try to imagine what it would be like to be near those planets, those black holes, those pulsars, and what you would hear, what you would feel. So I think this is a very powerful technique. It's a very powerful way to make people feel the universe, come close to the universe and try to understand it. And so I think this definitely has happened through those musical pieces that were produced. But what is also very important is that the artists themselves claimed that they discovered a territory which was completely unknown by them before, and they were actually deeply inspired and deeply impacted by this. And they said that they would carry this impact along to their next compositions. So they would constantly actually propagate this information, this feeling about space that they got through this. If you can move to the next and last overhead now. Okay, so I would just like to say that indeed these people went ahead, and this is actually describing what they did. Some of them, the first winner, Otto Vanki, presented his version at the Music Academy in Vienna, and began creating his first opera. And part of this opera would be this inspired by the sound of space. Antonio Sebran, which was the second winner, was hoping to perform live in astronomical conference, and he was working towards this direction. Susan Brewster, the third actually prize, has moved along, produced a much larger piece based on the original composition, and she is performing that in various places. She has also subscribed and visiting regularly the Royal Observatory of Greenwich, because she said that astronomy is now part of her life, the passion for astronomy, and so on and so forth. So other composers went ahead producing and being constantly inspired by space just on the basis of this single competition. Move ahead, please. Okay, so here is just a few words that I picked from the musicians who actually performed, who actually composed and performed this music. I'm just reading for you. The idea of connecting music and science was very exciting for me. In electroacoustic music, the borders of these two disciplines overlap, which reminds me of Pythagoras a few centuries ago, a few thousand years ago. From the first time I listened to their sounds, I could not get them out of my head. My composition was like a myth about evolution, randomness, and mysteries, but ultimately the fragility of life and our existence. Participating has certainly sparked off a creative path of discovery for me, and I'm very grateful and honored to have been included in this project. So I do hope that today we try to create inside you the same feelings about space by just trying to show you in a very quick way the variety of space scales, the variety of the objects that are found in the universe and the phenomena that are involved, and the music that is created, how the universe is full of sounds radiating these unique phenomena happening in every and single scale, and especially close at home in our solar system. Also because this is the school of Europlanet, where among other things, we are teaching on how to actually do outreach, how to transmit to people our passion about the universe. I think that today I've tried to show that one path to do this is actually excite feelings within humans. Besides the human mind, excite the feelings within you to actually make space very dear to you. And with this, I would like to finish. I'm sorry if I took much time. I think I did not record how much time I take, but I hope you still have some time to ask questions if you like, or to express yourselves and say your opinion about this. So thank you very much.
Thank you, Eleni. Anita, are you?
I am here. You just missed the round of applause that we were on mute, so I'm afraid you didn't hear that. We can do it again. There we go. I'm just going to draw some of the curtains actually, just so that you can see some of our audience here in the room.
Yes. Wow.
Okay. Good. So do people have questions for Eleni? Anything?
I cannot hear very well.
Who decided to create some music from sounds?
So is there anything? Any questions?
Sorry, it's been a long afternoon. I think it's been a lot of excitement. But I think Jean-Baptiste, were you going to say something?
Yeah. In fact, is there possibility with these songs that we learn something more than with the graphs that we can see the frequency represented by graphs during the videos, but by hearing these sounds, is it more clear sometimes to understand what's happening instead of just looking at a picture?
Did you hear that, Eleni? So because I heard not very clearly, the question is whether by hearing at the sounds, we understand better the phenomenon than by just looking at the pictures. Is that the question?
Yes.
So not really, and yes, actually. Okay, so no, for scientists, they don't need to hear the phenomenon in order to understand it, okay? So in principle, the sounds of space that I presented today are mostly related, I would say, to an outreach, so to try to reach out to the public, to people that are not scientists, and they would like to hear, to feel closer to what the universe is like. I must say that even for a professional astronomer to be able to listen to these sounds, it's professional astronomer is human, so it is a very exciting experience. It's not that it helps me to better understand with my mind the phenomenon or analyze the phenomenon, but it makes me feel closer to what the universe is, to what my place in the universe is, okay? So, but there is a but in this. So the first answer is no, we don't try to use sounds to better understand the phenomenon. It's because we understand the phenomenon that we can transform light to audible sounds and then hear it. However, it is true that recently there have been some studies, some publications, if you like, of people saying that, for instance, when we are trying to discover distant planets, exoplanets, planets orbiting stars far away, there are a variety of methods to do that, depending on how far they are, how visible they are, how big they are, whether you can record their spectrum, whether you can see them, which is usually not the case. You cannot image them most of the times. So there have been some studies saying that if you if you shift the light curves that you receive, like those two stars that I was talking about with the light curves appearing and disappearing. So if you try to transform this to an audible signal, you may be able to pick up something which usually may be lost in noise when you see an image, okay? But this is, of course, one study, one publication. Is not, I would say, a technique used by astronomers to better understand or to discover, in this case, an exoplanet. Okay? I hope I answered.
Yeah, that was perfect.
Okay.
Yes, please. Do you think that this method to look at signals as sounds could bring more people into astronomy, for example, blind people, and allow them to give or go to conferences and all this?
If I think more people to, you mean more these kinds of information, this kind of music to sensitize people, whether this will bring them closer to astronomy? Is that the question?
Allow blind people to do research in astronomy. For example, if they want to read a plot at a conference, they could not. But if at the same time the person who talks also plays the sound that goes with it and plots the curve or something.
Maybe I need a translation of this question. So the question is whether you can use information of sounds in a astronomical conference among professionals to better explain something. Is that what you're asking?
Yes, that, or allow blind people to read their data also.
So I think this is a question, right? So as I said, I am not aware of this being a methodology used in astronomical conferences among scientists to better explain something.
I think it's not just conferences that Nesh is asking about, just general for application. So the visually impaired people can then can hear the data rather than see the data.
Right. So I said, not aware of this being a common methodology among scientists. However, I do believe, if that was the first part of your question, that people listening to these sounds may be attracted to science, which ultimately, there are lots of intermediate steps, but may ultimately be interested in science and may ultimately become scientists. However, I'm not aware of this being a methodology, listening to sounds along with projecting diagrams or, whatever else to communicate science among peers, okay? I'm not aware of this being a common way of doing things. And I believe one of the reasons is that what you heard is a kind of very rough representation of waves. So people don't go to great detail or representing all the data in acoustic waves. I don't think this will add anything to the complexity or to the clarity of the data that we get. So these were just a rough representation of sounds, mostly meant to outreach with the public and not with experts. Did I answer, or maybe I didn't understand the question still?
Well, it has not developed yet. Maybe in future it will be developed, this method.
Maybe.
In fact, it has started already a little bit. I was in a conference in Potsdam, I think it was in May, about gravitational waves, and to introduce the conference, the speakers showed the graphs of the waves, and there was a sound, and the sound was really catchy because the frequency is increasing the more and more the black holes are orbiting to each other, and then at the end, when they collide, finally, it's getting really high. So it was really really great. And
yes. Well, yeah, I've also galaxies. So at the time we didn't do any music, of course, but I'm sure that if this was translated to sound waves, it would be quite an amazing sound made by two galaxies colliding. But as Grazina, I think, said that this maybe in the future people will think there is an added value even for science in translating their data into acoustic waves.
A question. Eleni, I have also a question for you. When you analyze those sounds, it is clear that space sounds are quite chaotic. And how do you think with time, maybe those sounds become more harmonic, or they are still chaotic?
I understood the question. You said that the sounds were mostly chaotic, some of them at least, and the question was whether
looking through the time, still since the Big Bang, are those sounds becoming more harmonic or still the same chaotic?
So are they becoming more harmonic, or are they still chaotic? The sounds that you've showed or played today are pretty chaotic.
It depends on the speed with which you are listening to them and on the time scale and with which we are hearing these sounds. If you hear only a small part of them without waiting for the repetition or the periodicity of the sound, and we said that the periodicity is very much depending on the phenomenon you are recording, very short and very large periodicities. So if you only hear a small part of them, then yes, maybe it is chaotic. But if it is a periodic phenomenon, then you can hear this harmonic coming back. Now, if it is also a violent phenomenon, like for instance a lightning, then of course there is very little periodicity, right? So then yes, it may sound chaotic or a momentaneous event, you know. So it depends on the sound, it depends on the time scale and on the phenomenon you are recording. Sometimes they sound chaotic, sometimes they're violent events, and sometimes they're repeated, like the pulsars, for instance, they repeated the periodic events. Okay, so of course then the human mind has to enter to actually discover the harmony, give it an extra dimension, if you like, which is also imagination, and then make a story out of it. And that's where these musicians came in. They took these sounds, which may sound chaotic or not, may sound violent or very calming, and then they gave it a third dimension, and then they make them sound less chaotic, more important, more calm, more chaotic maybe. They made them describe a story. I don't know if I answered, Grazina.
Yes, of course. I understand that we need more input of human to make all the world more nice.
Right. I think. Sorry, Talina. I think here we're. Any more questions? I think we're done. I think we're done here. So unless you've got any online, Talina.
No, good. So with this, I want to thank Eleni and the team there, Anita, Krasnia, and everyone who helped with the technical team there. And so thank you for joining. And I'm going to stop the broadcast and tune in for next month onwards. We'll have the regular.
Thank you very much for all this effort. I'm so sorry for not being able to be there. Thank you very much.
Thank you.
Okay, right.